Today what I'm going to talk about is making this random LED blinker. It's 5 channels, random per channel, using an Arduino Uno. And I designed it on Tinkercad. Right? It's homemade. I made myself a homemade shield. Those of you who know Arduino, you can stack shields on top of them. They're called their auxiliary boards that perform other functions. I'll hold it up later during the rest of the presentation. So that's what we're going to do. You start off, this is not about the programming. This is not a programming course. This is about the process, okay? Anybody who wants programming help, call me on the phone. Or any of these other people who know anything at all about C++, okay? It's 5 channels. This is the specification. There are 5 channels. Each channel is 10 each of 0402, that's 0.04 millimeter by 0.02 millimeter LEDs of a single color. So we have 5 different colors: blue, green, red, blue, green, yellow, white. I set up the blinker random, and this is important. Every time a channel blinks and turns off, both the turn on time, or the on time, and the off time are random on each channel, right? So it's between all of these things, we have 50 LEDs blinking, and in groups of 10, they're randomly blinking on and off, on and off. So I chose time periods between 100 milliseconds to 500 milliseconds is either the on or the off period, randomly chosen. Random on-off time, random timing between channels, and I call it the twinkle effect, right? If you arrange these LEDs on a Christmas tree, all right, they would just sit there and sparkle at you. Adjustable brightness, each channel independent. And I was given a spec of a 12-volt power supply, all right, to make all this work. LEDs 0420 are specified. They're, I'm sorry, inches. I thought millimeters. They're not. They're inches. No, that's millimeters.
Yeah.
At any rate, yeah, they're millimeters. I made a mistake. It's not inches. They're wide angle, no lens. All right, and there's 10 of them per channel. This, by the way, is what an 0402 looks like. Right? There it is. Right? So this is available for pass around so that you can try to take a look at it and see it. All right? So that's the specified LED. These LEDs that I made with the prototype are still 0402 chips, but they're in the regular housing that we're used to. Now the regular housing is, the chip is in a cup, and there's a reflector behind it, and you have a lens. That's why it's so big. All right, but it's the same size chip. The controller, had to have a controller. They were looking for small space, so we had an Arduino R3 or above. You can use a Mega, or a Raspberry Pi, and there's a bunch of other small little RISC computers that you can use. Power supply, 12 volts at 5 amps. And we'll call this a power supply LED power shield, 7 volts at 5 amps. And we have a little step-down regulator here to take care of that. All the switching transistors, there's high-speed switching, so we're using 2222As, little switching transistors. The potentiometers for setting the brightness are 10K film potentiometers, and everything is quarter-watt metal film resistors. Okay? So now we got to select the components. Each color of an LED has its own volts ampere characteristics. They're not all the same regardless of what you may think. They are similar, right, in that almost all of them at 20 milliamps or slightly above, they go poof, right, and they die. The perceived brightness of each color is more even around 10 milliamps. So in the design, what I said was, that's okay. That's going to be my brightest point, all right? So I designed everything for 10 milliamps through each one of the LEDs. So the design is for each channel is 10, for each channel is 10 LEDs in parallel, which is 100 milliamps. So it's 100 milliamps per channel. But let's take a look at the LED characteristics, because I said each color has its own characteristic. Here's your typical LED that you're looking at. You have this nice lens case around it. But the important thing is this is the chip, and it's almost to scale. It broke, I'm sorry, don't worry about it. It was only the handle.
It's only the handle.
All right. Just for your edification, we have the two leads. The cathode lead, right, is also called the anvil, and the anode lead, which is a longer lead, is called the post. And together, they, people have wrongly conceived that, oh, the lasing takes place between these little two, this gap in here, that's why. No, it doesn't. Okay? No, it doesn't. You can see that there's a connection in here, a wire connection. So that's the internals of a typical LED. On the end of that LED that's being passed around, right, this is that chip right there, all separated out, and they wire it up for you, which is good. Yeah, don't do it. Here's your typical LEDs. It goes from the infrared to the ultraviolet. These are typical in that the separation, the order of separation between them is the same. Where they fall on that graph depends on the manufacturer a lot. But the ultraviolet always has a large forward voltage, and the infrared always has the smallest forward voltage. So if you look at, for instance, 10 milliamps, which is where I'm going to be right here, and you come across and you say, well, that green looks like it's about 1.9 volts forward voltage, whereas the white way out here, right, is got 2.2, 2.3. Okay?
1.7.
Yeah. And that is the point of where these things first start to head up like this, is the point of lasing. That's when it starts to laze. As soon as it starts to laze, it takes more current. Because it's more energy, it's being turned into light. So that amperage is turned into light.
So as the current goes up, does it get brighter?
Yes.
Okay.
Right? Up to the poof point. They have 100 milliamps on this, and yes, they tested them, right, at 100 milliamps, but they floated them. How they tested that at that high current is they float the pan that the thing is in, right, in liquid nitrogen. Okay, so that's how they test it. That's how they test it and got these numbers. So they kept it alive, in other
There's
words.
one way to get past proof. Yeah.
Yeah, you can.
Otherwise it's dry and, yeah.
Well, the problem is it can't get rid of its heat fast enough.
Yeah, okay.
All right. It's not that it can't get rid fast enough is the clue. All right. Arduino outputs are 5 volts on and 0 volts off. Okay, that's your standard output. Arduino has an internal 5.5 regulator. It also has a 3.3 volt regulator on the inside of it. Our supply is 12 volts. So we want the LED power supply to be as low as possible, but above 5 volts. Okay? What we don't want to have happen is voltage regulators fighting each other. We can't have 2 5-volt regulators. They'll oscillate, they'll fight. So 2 volts is about it. That's about as close as you can get one regulator to another, because there's usually a pass transistor or some sort of switching device inside, and it has a 0.2, 0.3 volt drop across it. So you don't want to get into a hurt state. The Arduino outputs also only have a 20 milliamp max. I need 100 milliamps minimum per channel, remember? Okay.
Because you have 10 and
10 set at 10. Okay.
parallel.
Yeah, they're all in parallel. So, usual and customary design is to avoid the dueling regulators, 5 plus 2 volts or more, 5 volts on the inside on our outputs, 7 volts will be our supply for the LEDs. If we do some calculations, we have to supply a resistor in this string of LEDs for each color to take up the difference between the lasing voltage and the regulation of it. Okay, so, and that's true. You know you have to put a current limiter of some sort into an LED circuit, right? Unless your outputs are automatically current limited, right? That's another kind of circuit. A lot more components. Well, the problem is, if I need to drop a watt of power, right, voltage V squared over R, right, I times R, that's a big resistor, 1 watt resistor. So and because it's got a relatively small surface area, it can't be next to each other. A lot of them. So all this has to do with space of design, things like this, and thermal management, which is another thing that engineers are responsible for when they design. So instead, what I did was I used multiple 1/4 watt dropping resistors for the desired resistance. They themselves, if I use 2 or 3 of them for the amount of resistance I need, there's more surface area on all those resistors to get rid of the extra heat. This is also why we drop it down to 7 volts from 12 volts with a regulator, rather than having to put a great big dropping resistor in there. Believe it or not, the cost of the dropping resistors and the wattages at 12 volts down to the, 2.2 volts on the LED, right? That's a fairly big resistor. Costs a lot of money, and you have all that heat trying to get rid of through a relatively small surface area. So using multiple dropping resistors for the desired resistance gives you more surface area and therefore less temperature rise. So what do we have to do? The design steps. Remember I said that this clinic is about how to go about design. So we've taken our specification, we made our our component selections, and now we're have to make the design and build the thing. We've got to power an LED. We got to blink it without using the delay function, and this is important. In RISC computers, which is reduced instruction set computers, right? They all carry the same characteristic, and that is when you use the delay function, right, which is a C++ command, right, it stops the program counter. If the program counter stops, everything stops, right? So we have to use a different function, right, to count time. And basically what it is, when you first turn on a computer, somewhere inside, there's a counter that starts running. And what you do is you say, look at it now, compare it to this. And there's one more apparent programming step in there. Right? But you gain, but the program counter keeps running for the other channels that are working. Randomly blink on time, and I have equals off time. As it turns out, when you actually do the timing test on it, the off time is also random, even though you pick the same one. And the reason is because the computer is servicing the other 4 channels, right, all the time. It's always servicing the other 4 channels no matter where you are. So there's an additional delay in there. So it actually is fairly random. Put it all together. We need 5 channels of 10 LEDs per channel. So we want to design and build a 5-channel LED power driver using high-speed transistors in the switching mode, right? And we're going to use a potentiometer to vary the LED brightness per channel. Well, what's a method for doing this? I have an LED, and how may I change its brightness? Well, I can use a potentiometer maybe and vary that current around a little bit, more or less resistance, more or less current, right? Or I can use pulse width modulation. And pulse width modulation in an Arduino with 5-volt outputs, that LED gets 5 volts when it turns on through that high-speed switching transistor, 100 milliamps per channel. And at some time later, it shuts itself off. If it's on full, you see full brightness. You see 10 milliamp brightness per LED. But if it's only on half the time, your eye, okay, and your brain thinks it's dimmer, right? I don't know if any of you have ever been in your automobile, and if you have a rear view camera like I got on mine, and you look in that display of what the camera sees, some of the cars behind you, their headlights are going like this, right? Well, that's because those lights are being pulse width modulated so that they appear to the human to be lower brightness, okay? So in these LED lights on your truck or whatever it is, there's no high beam, low beam. There's only all the time or half the time. And it looks like it's 2 different brightnesses. You don't see it in your mirror because your brain keeps putting everything together. But you can see it on the screen blinking at you like this. All right. And we're going to use an LED to change the brightness per channel. Like I said.
Also because your eye can only resolve a tenth of a second.
Yeah, that's true.
So if you take an LED that's pulse width modulated, fix your eyes and you move your head across, you see a bunch of dots.
Right, you can see a bunch of dots. This is what I was talking about using delay. Okay. we're going to start, we have to start a millisecond or a microsecond counter. Not me. And we're going to use the millis function or the micros function to go out and acquire that time and then do a subtraction and compare to whatever we've set whatever the random number generator says is the amount of milliseconds between 100 and 500 milliseconds. And that'll change the state. This is Arduino programming note. Don't use delay. Right? I've taken delays out of everything. To facilitate having to constantly rewire Arduino, anybody ever played with Arduinos, you have a pegboard that you use to prototype your design with. Such a pain for all of this stuff. Right, so many configurations. So I chose to utilize a virtual CAD system offered by Autodesk, and it is Tinkercad. Okay. So let's go out to Tinkercad. Come on. Why did it not go?
You want to right click on it?
I did right click. Here we are. That's a link and it's not going to it. There it is. So that's because of Edge. I hate Edge. So it just took a while. Goes out to Tinkercad. Well, what is Tinkercad? Tinkercad is made by Autodesk. It's free. And you can design so many kinds of different things in it. You can design electronic circuits or mechanical devices or whatever. It's really a pretty good platform. So I used it for Arduino. And I sure hope it logged. It has a bunch of stuff already on here. And there I am. So it found me. Okay. These are all my circuits. All right. So going through the design process, right? What's the, I should be able to go put this guy down and see where I am. Just for a second, Tinkercad. Okay. This would be the circuit for each one of the channels, all right? Where we have the 7 volts. This happens to be white. It's actually 2.84 volts DC, right, at 101.5 milliamps. It's around 100. Right? And what I need is, and don't forget, there's a drop across here, which is about 0.2 of a volt. So we're taking out from 7 volts. We have to go down to subtract 2.84, and then subtract this 0.2 in here. That the switching transistor, when it's turned on, is. And you have to do that for each channel. Right? So that's a lot of power. Right? So let's go back. Let's see. Where's the change?
On your keyboard. Your keyboard with the.
So, what's the first thing that we have to learn how to do? We have to learn how to turn on an LED. All right. So we'll go to this one, and we're going to tinker this. We're going to play with it. And this is very simple, right? Very simple. Here's your Arduino Uno. I am using the digital output, and in the code for it, it says blink this thing on and off. There's a typical resistor for what I need. Gee, now what's that? Brown, green, brown. How do we get here? Right? Over in this panel over here, you can find all the components that you need. This one says Arduino. And here's all the different Arduino models that you can pick. And when you want one, you say, oh, I'll try this one. You can just bring it right over here, and there it is, okay? You can also click on it and delete it, I hope. It's hard to read from this angle. So, you can pick this. You can pick all your components. And look at the components that are available. There's resistors and capacitors and what's that guy over there? I can't read it. Okay, yeah, electrolytics. There's all kinds of diodes. And when you snap on one of these things, it gives you a whole list of all the kinds of things that you want. You can call the particular type of diode up and it'll stick it in. It also sticks its characteristics into the computer that's running this. This is being run on Autodesk's computer right now. So this is just a, but you have all kinds of sensors, and you know, there's ultrasonic things. There's all the kind of things that are, but these are ring LEDs. It's just keyboards. You can pick whatever you want and shove it onto here and then just wire it up. All right? And of course, how you wire it is you click on a wire, you know, and you, and look at that. It tells me, it says, oh no, you're not quite lined up yet. Come on. Let's make this guy. See, now you get the two blue lines, and it tells you that you're nice and square. Okay, so what's this thing do? Well, up here you have a section called code, and this window comes out and it's blank, and you write your code in there, right? Now this guy, let's see what he says. He says that we're going to come out of pin 2. It says constant integer LED pin 2, and there he is, right on pin 2. Initial state when you turn it on, it's off. We set up our count, our test here. There's two places in programming. There's two types of variables. Well, there's a whole bunch, but there's two major kinds that you can create. Some are global, which means it applies to every location inside the program, and some of them are local, which means it's only applied inside a loop someplace. And so what we do is we assign our timing, millis, current millis, and it says go out and get the millisecond count. And it performs a test if this is in there, right? And if that's correct, if it says if LED state is low, the LED is already off. Therefore, turn the LED state to high, which turns it back on again. Okay? Otherwise, leave it alone. And then it says go write that out to that pin. So it's going to turn that guy on and off. All right? So this is just turning it on. So what we're going to do is going to get rid of this guy. Yeah, I think you're right. And then we're going to start the simulations. As a matter of fact, I'm going to get rid of this guy too. And we'll start the simulation. You see the power come in and plug it in? And look at that. It starts blinking. Everybody see that? So, you do it without having to play with wires. Right? You had to write the code anyway. But now you can simulate it and get it to work. Okay. So,
If you do something wrong, we'll start smoking
If your resistor's too small, right, it blinks once, right, really bright. and it tells you that you have a fault. Okay, so this was blink without a delay, without using the delay function. This is blinking using the millis function. Okay, let me go back one more. So after we've learned how to do that, okay, notice it always takes the last one, it moves the left to the front of the line here. What's the next thing we want to do? Well, let's change the intensity by introducing pulse width modulation. Now, in this one, it's basically the same. I used a blue LED. It's got the same 470 ohm resistor in it. This time it's coming out of pin number 3, and the reason is, see the little dash mark? 3, 5, 6, 10, and 11 are all pulse width modulation capable outputs. Okay? So I had to go from 2 to 3. And the potentiometer is hooked up to an analog input. See, it's on A0, analog in. The analog in and the pulse width modulator out, believe it or not, are 2 different sizes. So one is 256 bits, and the other one is only 128, or, yeah. So if you don't account for that change, and this is why you have to know all your components, you're going to wind up with the thing not working. So let's just take a look at the code. Now, we should be able to do this. Okay. Now this one is even less. It's only 13 lines of code. It's less than the last one. Okay? And the reason it is because I'm using a different, I'm sorry, it's 1024 and 256, right? I'm using a different way to change the state. The state is on. All I'm doing on this one is changing the intensity. So we had the blinking without using the delay function. This is now changing the intensity. So what do we do here? Well, we're going to input the potentiometer value, right? And it says analog in is 0 to 1024. So all the way to the left on the pot is 0, all the way to the right is 1024. And it's a number. It's a digital, it's an analog to digital converter. Now, our intensity brightness value, I have to take the pot value and divide it by 4, because the pulse width modulation output is only a 256 count output. So you divide it by 4. And then you write that number, whatever the pot is reading, divided by 4, out to the brightness. And the brightness pin is pin 3. Okay? So let's simulate that and see how that works. Oops. Control. I'm using the control key, by the way. Control mouse is your zoom, right? On all of Windows 11. Okay? So let's get rid of this. We'll make this guy, let's get rid of this. Make this guy a little bit bigger. Okay, and watch for the power to be plugged in. I love it. Start simulation. Oh, power got plugged in. Wow, oh, it's not working. Your pot's set at 0, people. You get what I mean? Let's go set it over here. Oh, come on, there it is. You see the brightness coming up? Okay. Oops, come on. There you go, there you go. There you go, it's still on. Shut it off. Now it's off. Full on, come on. Okay, looks like it works. So now we know how to blink it, and we know how to randomly blink it and how to change its intensity. We just put it all together. Okay, so we'll stop it. We have to unplug it. All right. Let's go back to where we were. So here's so it moved it to the front again, you see. Now we want to, let's randomly blink 5 of these things. All right, we know how to do that. So we go to this one, so then I went here, tinker this. And sure enough, I've got 5 LEDs and I've got 470 ohm resistors. These are my 5 outputs, right? This is just randomly blink. Now we want to randomly blink these, okay? They're getting full power. There's nothing in here. There's no analog input for pulse width modulation, right? So all of these outputs here, 2, 3, 4, 5, 6, are bang, 5 volts on, that's it. Or this is just but using the random function. So this is our last piece that we need. So if you want to take a look at the code, because I got 5 of them now, you got a lot of stuff going on. All right? A lot of repeats. I didn't want that. Get rid of that. So we're just defining a whole bunch of variables here, the on state. And now the setup is things that are set up globally. Okay? And if you look down in here, now just because it's set up globally to begin with, all right, this sets their state is what it's doing. It tells you that if I have a random number generator, I have to seed it first. I got to give it something to begin with. Well, what's random that I can give it? You notice it says the seed is for an analog read on channel A0, but nothing's connected to it, right? What do you get in an A to D converter when you turn it on and you have no input?
0.
0 is not grounded. If your input on your A to D converter is grounded, right, it gives you 0. If it's open, there's numbers jumping all over the place. The computer goes out and just says, okay, I'll write that into the random number generator as a seed. So it's random, really random. All right. What are we doing here? Let's just look at one of them. This one happens to be for the red, right? So it does this comparison. If the current millis function, is less than, because it has something in it now. The random number generator's got something in it. If it's greater than or equal to the interval, which is what it is, then do this, right? We're going to write to the red LED pin. Okay. And this exclamation point is basically a knot, right? Okay. It sets up the previous one, right? It sets up the interval random. There's your random. See it? So that random number generator is just running, right? And at this instant, it picks one. It says, go pick it, right? And it does that for all 5. And then it should write out, where are they? When we write it out, oh, yes, right here. This is a digital write. It writes to the pin, right? Whatever that random number is. So, and you do that, what, 5 times, right? This is white. This is yellow, green, blue, and red. Let's see how it works. Now, if you can find a pattern in there, I'm impressed. Yeah, wave off, right? So now we've got all 3 of our design or operational functions designed, right? So we can blink an LED on and off, we can change its intensity, and we can randomly change its on and off interval. So we have all 3 of them. Let's just put it all together. And sure enough, it should be this one. And here's in order to make a prototype, everybody at least had a chance to see the LED, right? Okay, it's really tiny, right? If you guys want to follow along, these are handouts that contain all the code and everything else. Whole bunches of information in there. So let's see if this guy works. So, oh, by the way, here's a new component you haven't seen, right? That is our 7-volt power supply, all right? Remember I said we have to have 7 volts? The 12 to 7 isn't shown, right? That's something you buy off of a shelf, right? So this is going to be 7 volts. So here what we have now is we actually have a working model of how the thing is going to be. There's 10 reds and 10 blues and 10 greens and 10 yellows and 10 whites up there, all right? And after you work out all the math, these are the 5 transistors with an N telling you it's an NPN transistor, right? Here's the 5 potentiometers giving you the pulse width modulation, which is the intensity, all right? It's all wired up. It's all in the thing I handed out there. So we've got to put all the stuff together, and when you put it all together, all right, it looks like this. This is where you declare a whole bunch of stuff, what the on states are, and give them some names to things, and tells you what type these are. Unsigned long integers are big, all right? Now, even though this thing has a random number, or a clock that we started, the millisecond clock, and the microsecond clock, which is 1,000 times as fast, right? It's finite in length, the number of bits. So the clock that you're choosing your millis and your functions with will overflow once every 41 days and something like that. But all you have to do ever is turn it off and turn it back on again. Now, in the Arduino, the latest Arduino update, the programming software update, they took care of that. In the interpreter or the compiler, they added in a function, the part of the function to reset the clock rather than just overflowing and causing an error. So that's fixed. And here's where you set up what things are inputs, what are outputs, the intervals for the timer, right? And we start. Okay. Now let's just take the red. All right. What do we have to do? We're setting up the timing. Okay. This is the initial value. We go out and we write it. See, initially it's low. It's defined as low, right? Else, we go out and we put in a lower value, right? Here's the random function generator. The random number gets in there, okay? So that's all there is. You say, well, that's relatively easy, right? It's not very much code to have all three of those things, all three of those functions in there. Oops. It's not that big. You know? So here's white, for instance. That's it.
The nice thing with that is that once you've done the red one,
Yeah.
you just copy the code and change the color.
There you go. So the programming time actually isn't that bad. It's another 3 minutes if you just did it for one.
You do find and replace them?
Yeah, you do find and replace. So the code is in there. It's rather simple. So we're going to put this back. Now we're going to see whether this thing works. Now don't forget, it's also in the computer. It is firing these transistors, right? So let's start it. And sure enough, there they are, randomly blinking. Oh, let's take, oh, is it really blinking? Let's take the white one and turn it way down. You see how it's changed? All right. Let's take the green one and move it down. See how dimmer, it got dimmer? All right. Anyway, it does work. Ooh, come on, red. Now, don't forget, some of these delays that the random number generator picks, right, are relatively low, 110 milliseconds. It's 1/10 of a second. The reason that you don't see some of these things blinking is it's got to go all the way out to Autodesk's computer and come back again over the internet in order to tell this copy of their program to change that value. Okay?
So they don't put any functions local, do they?
No.
This is like a remote interface up for the...
Yeah, it's a remote interface is what it is. Okay, so now we want to see the thing really work. All right, so what I had to do was for this design right here of the LED board, all right, I took a breadboard, I mounted all the 10 LEDs, 5 channels, right? And I wired them up in parallel and brought them out to this connector. So this odd one, the odd connector out to the side is the ground, right? And the others are the power. right? Not easy, not hard to do. This was all done with wire wrap, okay? Remember that technology? All right. The next thing we needed was, to be able to power this, was the 7 volts, and that's real easy. This is a 30 volt max down to about 3 volts. This is as low as it'll go. Voltage converter.
You can pay for that on Chemo.
This thing,
Yeah.
it was like $6 maybe.
Nah. I bought 5 for $1.28 a piece.
No, no, paid like $6 for it. Actually, well, okay, so let's hook all this stuff up together and see whether we really get random linking here, because then we will not have the delay of the internet.
They were about less than $2 a piece.
So, oh, by the way, I also bought a shield that was a breadboarding shield, right? The only things that are connected through the pins are the power supplies, okay? So you've got your 5 volts and your ground and all that stuff, right? And so you can pick your inputs and outputs and wire them off of the pins, right? And these are the same pins that are on the Arduino. These are the dropping resistors, your potentiometers, and your 5 transistors. And this was all wired up with wire wrap. And those of you who don't remember or want to see the wire wrap, there it is. Okay.
Okay.
I don't know if you can zoom in that far on it. So this was all done with wire wrap. Better than soldering all that stuff, eh?
Yeah.
So we'll put it all back together again. Well, way back when, I had a job working for the telephone company doing wiring. And we use wire wrap. All in. For local stuff, you use what's called the punch-down blocks. The 66 blocks. But for inside an exchange, right, like a ESS 5 machine, it was all wire wrap.
Yeah.
All right, so let's see if we can't get this guy going. Out. Yeah, make sure the output goes in here. And what I did was to assure that there's a male and female connectors.
So if you connect to itself.
If it's long enough, it can.
If it's quick enough, you can keep all those little electrons going around. There we go.
So, sure enough, here's our 7 volts that we said we had to have. We have a 12-volt wall wart giving us power. We send it down to 7 volts. And sure enough, we are randomly blinking all 5. Now, can we change the intensity? Right?
I'm going to say yes.
Well, let's just look at the white, for instance. You think it changed the intensity?
Absolutely.
Now, if you get it too low, it will stop lasing. Barely on. There it is. Okie doke? Well, let's try green's another good one because it's nice and bright. All right. So you can see how just by changing the this analog input, right? You can change the intensity, right? Let's try the blue. That's always a nice one. See? Blue's kind of intense, isn't it? Yeah, yeah. All right, so as I said, randomly spacing these things like on a Christmas tree, right? You can, with an LED that's that size, wherever it went, it's probably blew away in the wind, you can, at different scales, even at N scale, you wouldn't have so many, but you could even do it at N scale, blinking a Christmas tree or any other random blinkers.
Heck with that little one, do it at Z scale. That was
Yeah, they're very tiny. That's okay, those things are only pennies a piece anyway. Okay, so, Tinkercad also gives you the schematics, right? Gives you a full set of schematics. There it is. Random blink, 5 channel times 10 per channel. All the connections, blah, 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 blah. Names everything for you. Gives you a bill of material. Yeah. Thank you.
All free.
Is there any, wait a minute, there's supposed to be something special happening here. There you go. Does anybody have any questions about this presentation?